Hello everyone. In this video, we are going to learn all you need to know about the moments of inertia, starting from second moments of area and then going to moments of inertia and parallel axis theorem, radius of gyration, and so on. And most of the material, especially pictures, are taken from Engineering Mechanics Statics by Bedford and Fowler. So if you remember when we talked about the centroids, when I showed you the formula for x bar, I said that x bar is integral of x dA, correct, over A. And this one, if you remember, I call it the first moment of the surface with respect to the y-axis. And similarly, where I have y bar, that was integral of y dA over A. That was the first moment of the surface with respect to the x-axis. So these are the first moments or first order moments of the surface. Now we also have second moments. That's where these x's or y's are power 2 or they are multiplied together. So we have ixx. Now some textbooks, they just use ix as opposed to ixx. So you might see ix or ixx. That is the distance to the x-axis squared. So y squared dA. And similarly, iy or iyy, which is integral over a of x squared dA. So these two are called the second moments. And there is also a product moment. So this is called the product moment, which is integral of xy dA integrated over the whole surface. And there is an extra one. Let's talk about this one as well. This is called the polar moment. So this is called the polar moment. And so your element dA, instead of squaring its distance to the x or y axis, you square the radial distance of it to origin O. You square that, rx squared. And you know r squared for a 2D surface is x squared plus y squared. So the polar moment is basically, if you can see this first portion of it, integral of x squared dA. That is your iyy. Integral of y squared dA is ixx. So we can say that it is summation of these two second order moments. Okay, so as I said, this is called the product term. Good. So these are new terms. Now, this first moments, they could be positive or negative, depending on whether your surface is on the right side of the x-axis or left side or above or below, right? Then you would have different things. For instance, for this surface here that is in the first quarter, both of them are positive. But if you bring it here to the fourth quarter, now your y's are all negative, x's are positive. That means this first moment is going to be positive, this guy is going to be negative. And if you move it to the third quarter, both negative. You move it to the second quarter, the first one is negative, okay? So they could be positive, negative, or if it's perfectly symmetric with respect to, let's say, y-axis, then here this one here is going to be 0 because you have positive x, and for a's positive x, you have a similar negative x. So they could be positive, negative, or 0. Now, for the second order moments, that's not the case. Here, you are always multiplying a positive number by the area, which is also positive. So this guy is always bigger than 0, and this y is always bigger than 0. So these two basically moments, principal moments, ixx and yy. And by the way, that's not exactly principal. We'll talk about principal later. But these two are basically your positive numbers, always positive. What about the product? Now, product could be positive, negative, or 0. For instance, again, if it's in the first quadrant or the third one, product of xy is positive because either both positive or both negative, which means, again, the product is positive. But if it's mostly in the second or fourth quarter, they could be negative, or if most of it is in the second or fourth quarter. So this number could be positive, negative, or 0. When can it be 0? When the part is symmetric with respect to x or y axis. Because again, if you look at this part here, this dA element has a negative x and a positive y, while this one, right mirror image of that, this one has both positive. So when you add this xy dA for these two, assuming that they have the same dA, they would cancel each other, so that could be 0. The same thing goes here. If it's symmetric with respect to the x-axis, again, you have this element here and this element here. This one, again, both x and y are positive. While this one here, it has x positive, but y negative. Again, it could be 0. So if the area is symmetric with with respect to either x or y, the product term is always 0, but it could be, as I said, positive or negative or 0. But these principal ones, as well as this polar one, which is some of those principals, they are always what? Positive. Okay? So that's the first thing. What's the unit of them? Well, if you look at the units for all of them is the unit of length to the power 4, correct? Because what you have is a distance squared times an area. So the unit for all of these is something like meter to the 4, or millimeter to the 4, or feet to the 4, or inch to the 4, anything like that. Okay, that's the unit for second moments of area. Now, similar to the idea of centroid for first moments, we have a new idea called radius of gyration, or K, which is for second moments. What does that mean? Well, if you remember when we talked about first moment, what was the idea of centroid? We said that instead of having the actual surface and finding these two first moments for it, what we can do is we can squeeze this entire surface into a single point and put all of that area, squeeze it into that single point and put it in this location x bar and y bar. Then the first moment of the single point with respect to the x-axis, which is a times y bar, and with respect to the y-axis, with respect to the that was for x, and with respect to y, it is going to be a x bar. These two are going to be the same. And from there, we divided both sides by a, and we got the formulas for the centroid. Right? So centroid is a point that if you squeeze the whole area into it, the first moment that it creates is the same as the actual surface. Now, similarly, we can have a similar notation for the second moments. What is that? So here, what we do is we are going to, again, squeeze the whole actual surface into a single point. So this is the actual surface. Again, we squeeze it into a single point, put all the A in there, and the distances of that basically surface or a small point that has all the surface in it with respect to the y-axis and with respect to the x-axis is what? So this distance here, we are going to call it kx. And this distance, we are going to call it ky. Okay? So pay attention, this time the order of x and y is backwards. The horizontal one is ky, the vertical one is kx. So now if this one has this ixx, which is integral of y squared dA, we say this small single point surface will have the same moment as this one. So what is for this? In this case, the distance you have from the x-axis is a times kx, the distance, the whole thing is squared. Because there is only one point, there is no integration, it's just a single point. So we say these two are equal. And similarly, Iyy, which is the integral of x squared dA, we say this is the area times the distance of A with respect to the basically y-axis, right? And the distance of A to the y-axis is ky, so it's going to be ky squared. So if you divide both sides by A and take a square root, then you have these radius of gyration definitions, or these are the square of them. So the radius of gyration x squared is square root of, or not the square root of, ixx over a, or if you want the kx is square root ixx over a, and similarly ky is basically square root of iyy over a. Okay, so these distances, we call them radius of gyration. We can define a similar thing for the polar moment. We say the actual polar moment is equal to some radius of gyration from the origin times square times a, and since this one is ixx plus iyy. Okay, and this ixx is basically kx squared times a, and this guy is ky squared times a. If you simplify a from both sides, you see that ko squared is kx squared plus ky squared. So the polar radius of gyration is the sum of the x and y radii of gyration. So we get something like a Pythagorean theorem. And so that is it. Now, what's the unit of this k? Clearly, the unit is the unit of length. Why? Because this guy is L to the 4. This is L squared. So division is going to get L squared, and this is kx squared. So unit for both kx and ky are what? Unit of length, like millimeter, like inch, like feet, or meter, or something. So they are really some physical distance, because you see their unit is unit of length. Okay? Now, what's their physical meaning? Other than, of course, squeeze it and everything. So if kx is bigger or smaller, what does it mean? So a bigger kx means a bigger ixx, and a bigger ky means a bigger ky. Now, what does a bigger ix and iy mean itself, right? If this number gets bigger or smaller, what does it mean? Well, here you can say that if ix is getting bigger, means your points have a bigger distance from the y-axis or x-axis. And if your iy is bigger, means your points are further away from the x-axis. What does that mean? Well, let's go back and look at it. So if I have two different shapes, and they are both rectangles, but they have the same area, but one of them is like this. Look, one of them is like, for instance, let's say 6 by 6. The other one is like this. This one is 9 and 4. So the area of both of them is the same, right? 36. Now, remember that this is the x-axis, this is the y. So if I say which one of them has a bigger ixx or which one has a bigger iyy, what would you say? Without knowing the formula for it, because we're going to develop formulas for them. But if I say which one has a bigger ixx, so if I call this ixx1 and I call this ixx2, which one is bigger? Remember, this is integral of y squared dA, and this is also integral of y squared dA, but y here can range anywhere from what? From negative 4.5 to positive 4.5. While here can only go negative 3 to positive 3. So in general, although they both share the same area, elements here can have bigger y distances compared to here. It's further stretched along the y than this one does. So without even calculating, I can tell you this one has a bigger ixx. On the other hand, if I want to calculate iyy, here your y can go from iyy. Remember, what is iyy? Iyy is integral of x squared dA. So here your x can go negative 3 to 3 for the left side. Here it can only go negative 2 to positive 2. So this right one is not as a stretch in the x direction as this one does. So I can say if this is, the left one is iyy1 and the right one is iyy2, it's probably that this time IY1 is bigger. And we're going to develop formulas and we're going to exactly get the numbers. But since the areas are the same, and one is more stretched in one direction than the other one, I can see these kind of differences. Okay, so it kind of shows you the stretch in which direction. And what does that mean in real world? Where would you use it? We'll talk about it. When we get to the moments of inertia, I'll talk about where you would use them, right? In real life. Yeah, I mean, it means more stretch along X or Y. Fine. Where would you use it in real life? That's a separate story. And we're going to get to it. But let's move on. And to practice what I just said, here is a rectangle with the height of 2h and the width of 2b. And we want to find the formulas for the IXX, IYY, IXY, and the polar moment, as well as the radius of gyration. And there is one term here that you see I mentioned, and I call it the moment tensor. So what is this? When I say the moment tensor, or the moment matrix, you might be calling it, is a matrix formed by these components. So the moment matrix, in this case, since it's a 2D example, is going to be IXX, IXY, IYX, and IYY. It's a 2x2 matrix. In 3D there is a Z, so it's going to get 3x3. But this is called the moment matrix or the moment tensor. What tensor is that? If you watch my video that I have, I guess it's under playlist statics. It's called, is it a tensor or something else? Or is it a vector or something else? This is a tensor. This I is a tensor, and it's a rank 2 tensor. Because it has two directions. By the way, IXY and IYX are the same thing. Because whether I say integral of XY dA or I say integral of YX dA, that's the same thing. So it's basically, this matrix is always symmetric. Okay, so what I need is to find this matrix, for which I need to find these three components, right? This one, and this one. And also I need to add IXX and IYY to get JO, and then I can find those radii here. So let's go ahead and calculate this. How do we do that? Here we're going to directly use the integral formula that we had, and you're going to see for a rectangle it's extremely simple. The integration, the element that we use, is going to be very, very simple. How? So let's look at the first one. IXX. What is IXX? So IXX is integral of y squared dA. And it's taken over entire A. So we have to take some element, some differential element dA, and move it over entire surface, so it sweeps the entire surface. And hopefully if we can keep the y of it constant. If you don't know what I'm talking about, please go back and look at my video for centroids. You'll see what I'm talking about. Then calculating this will be very easy. So what I'll do is I move up from the x-axis by a distance y. I give it a thickness dy. And this small bar is going to be my element. Now, what's the area of it? Well, the area of it is the length of it, which is 2b times thickness of it, dy. So dA is going to be 2b times dy. So let's plug it here. Y squared times 2b and then dy. And if I want this span to sweep the entire surface, y goes from here, which is negative h, to here, which is positive h. That's all it is, calculated. So 2b comes out. Integral of y squared is y cubed over 3. You calculate it as h and negative h. So you're going to get h cubed over 3 minus h cubed over 3. You're going to get 2h cubed over 3 times 2. you're going to get 4b and then h cubed over what? 3. Okay, 4b h cubed over 3, where b is half of the width and h is half of the height. That's all it is. Now, in some books, you might see a formula like basically bh cubed over 12. And you might say, are these the same? Yes, they are. In those books, b is the entire width and h is the entire height, not half of it and half of it. If it's half, if the entire thing is b and h, then that will be simplified to this. Why? Because each one of them will be half of that, so you're going to get a 1/4 and another one, okay? And you're going to get this guy right here. Basically, you get a 1/2 and then 1/8, 1/16. Simplify 4 with 1/16, you get 1/4. 1/4 times 1/3, you get 1/12. So that is your what? That is your Ixx. Now, similarly, we can go about Iyy. This is integral over a of x squared dA. Again, here, if I can pick my elements such that x of it is fixed, that will make life a lot easier, and I can do that. All I need to do is to move the distance x from origin to one side, let's say here. So this distance is x, and the thickness of this guy is dx. So in this case, this element, the area of it is what? Is the height of it, which is 2h, times the thickness of it, which is dx. So this is going to be the integral of x squared and then 2h times dx. And for this to swipe the entire surface, it goes from negative b to positive b. And very similarly, you are going to get 4h b cubed over 3. So you see they are very similar, except one is power 1, the other one is power 3. Here they are swapped. Now, interesting thing is this. Look at that. Which one of them plays a bigger role? The one that has power 3, of course, right? For the x-axis, for this, which one of these two dimensions is the distance, is representing the distance from the x-axis? Clearly h. The bigger the h, the bigger the elements are placed from the x-axis. So you see h has power 3. So if you make this rectangle 2 times wider, I is going to be Ixx is going to be 2 times wider. But if you make it 2 times taller, I is going to be 8 times bigger. Similarly for Iyy, b is representing the distance from y. So you see power of b is 3, power of h is 1. Okay, so if you make this 2 times wider, Iyy is going to get 8 times bigger, but Ixx is only going to get 2 times bigger. So these are what? Ixx and Iyy. Now clearly, because your shape is both symmetric from x with respect to x and y, there is no question that Ixy in this case is 0. And Jo, the polar moment, is simply sum of these two. So that should not be very hard. You just factor out 4 over 3hb, and it's going to be h squared plus b squared. And that is your polar moment. So now that you have Ixx, Iyy, and xy, you can form your tensor. Remember, your tensor was this. And since xy and yx are the same, so I can just place Ixy here and then Iyy. There we go. That's your tensor. And what are the radii of gyration? Well, we can find them. So what is, for instance, kx? Remember, kx is square root of ixx over a. That is going to be square root of that whole thing, 4 over 3bh cubed, over what? A of this is 2b times 2h, so it is 4bh. We'll simplify a b, a 4h, and you're going to get h squared over 3. Simplify it, you're going to get h over square root 3. And similarly, if you do a similar thing here, you can see that ky is going to be b over square root 3. So you see, your radii of gyration are also proportional to those important dimensions. So that is our first example. The second example, which is useful, and I want to talk about it before we go to more important thing, is sometimes your shape is basically a circular shape, an arc. And if that's the case, well, clearly, if somebody says, what is IXY, again, the shape, this disk is symmetric with respect to with X and Y axis. So without any calculation, IXY is 0. No calculation is needed. Okay, done. Now, here, I would like to calculate the polar first. Why? Because if you look at the polar, the definition of it was integral of r squared dA. The integral over all a. So what you needed was to pick any element anywhere at radial distance r, and move it such that it takes the whole thing, right? In this case, your small r, the radius, should go from small ri to big ro, inner radius to the outer radius. Yep. So if I want this dA to basically cover the entire thing, the only question is, what kind of dA would you consider? Would you consider a rectangular element? The answer is no. Just like my video on centroids, here we have to use a polar element. So you go to radius r, then change the angle to theta plus d theta, and change the radius to r plus dr, and use a polar element. So if you watch that video, you are going to remember that. So again, you go to r, and with angle theta and with radius r, then you increase this by dr, you increase the angle by d theta, and then what? You connect them together. So this is your dA element. And this extra angle here is d theta. So if you remember, dA was r dr d theta, or dr times r d theta. So here, this is going to be integral of r squared times what? R dr d theta. And here it's all product, so I can separate this, make it a double integral, make it the product of the two integrals. Let's see, there we go. Now, if I want to cover the entire surface, theta goes from 0 to 2 pi, and r goes from small r to capital R, or ri to ro. And clearly, this is going to be r cubed, so it's going to be r to the 4 over 4. So it's going to be ro to the 4 minus ri to the 4, the whole thing over 4, and multiplied by, this is going to be theta, it's going to be 2 pi. So they're going to be a 2 and they're going to be a pi. So this is going to be your JO. Okay? Now, if it was fully solid, where Ri was 0, then you would get pi r squared, r to the 4, over 2. So this is what? This is for a solid disk with no hollow circle in the middle. Some books use it as a diameter instead of radius. So for r, you have to plug in d over 2. Then you will get what? Get pi times d over 2 to the 4. So you get d to the 4. And then you get the 1/16 over 1 over 2. You get over 32. Okay? So you can write it this way as well. So the polar for a solid circle is pi r to the 4 over 2, with in terms of diameter of it is pi d to the 4 over 32. But that is polar. What about ixx and iy? Now this shape is symmetric with respect to both x and y axis. What's the meaning of that? The meaning is ixx should be the same as iyy, because the shape is symmetric for both with respect to both axes. And remember that ixx plus iyy was what? It was jo. And I have jo. Since they are equal, then each one of them should be half of it. So ixx equals iyy equals j over 2. So it is going to be pi over 4 times RO4 minus RI4. There we go. Did I need to calculate those integrals of x squared dA and y squared dA? No. Because if I had to do it, then I had to replace x by r cosine theta, and this one by r sine theta. And when I integrate, I have to integrate here, instead of just d theta, I have to integrate sine squared d theta and integral of cosine squared d theta, which I have to do a little bit, basically manipulation to get that. And I can do that, no worries. But here I'm using the knowledge that I have and say they are equal, and some of them is JO, so each one of them is half of it. If that's the case, then for a solid disk, ixx and iyy are going to be what? If ri is 0, then they are going to be pi r to the 4 over 4. And in terms of diameter, they are going to be pi d to the 4 over what? 64 for a solid one. And if you go down here and look at the moments of important shapes or well-known shapes, you can see that here. Look. For a solid disk with diameter d, look, ixx and iyy are both pi d to the 4 over 64. And for a rectangle, it's bh over 12 and h cubed over 12 and b cubed h over 12. Those formulas that I told you, you're going to see if b and h is the entire width and the entire height. So you see, this whole height is h, the whole width is b. And this is the one for the disk that we just derived. And then here you have it for a quarter circle and you have it for a triangle. Okay, and these are very interesting. And you see, for a triangle, it's like a third of the rectangle. And for a quarter circle, depends on where you put it. And here, by the way, you might say, where is this point? This origin here is where? I mean, in these three scenarios, the origin is in the middle of the shape. What about these guys? The origins are where here? This G and this G, where are they? These are the centroids of those shapes. So this is the centroid of that rectangle, triangle, and this is the centroid of the quarter circle. So these moments are calculated with respect to the axes that are passing through what? Through the centroid. Okay? And these are calculated with respect to that. What if they are not passing through the centroid? Then we use what we call parallel axis theorem, and I'm about to tell you in like a few minutes from now. Okay, so these are all calculated with respect to axis passing through the centroid. And there is more. This table can be extended to a lot more shapes, but these are the most well-known shapes that you have. Okay, now that we learned about calculating these second moments of area and so on, and we learned that they kind of show the distance from the axes or stretch or something squared, what's the physical meaning of them? Where would we use them? So here we go to the next topic, which is called moments of inertia. Their definition is very close and very similar to those moments of area. They are related to each other, and these guys are resistance of the object to rotation. That's why we call them inertia. Just like mass, if an object is heavy, when you apply a force to it, the acceleration that it will get, which is F over m, is going to be what? It's going to be smaller. So a heavier mass is going to have a smaller acceleration. So mass is also an inertia term, correct? Inertia against what? Inertia against pushing or pulling. Inertia against translation. Okay, so mass is an inertia for translation. Similarly, if I have an object and this object has a bigger I, what I, we'll talk about it, I about the axis here. If it has a bigger I, let's call it IZZ for instance, if I apply a torque to it and try to spin it, this torque divided by that I, this torque divided by that I is going to be the angular acceleration of the object alpha. So the bigger this moment is, the slower it is going to start increasing or decreasing its RPM, or its angular velocity. Okay, so bigger moment means it doesn't like to be spun. It wants to not be rotated. Okay? Yep, so these are resistance to rotation. Now, what are these guys? If you look at this moment of inertia here, and this is the 3D version of it, this is assuming that there are 3 directions, not just 2. Clearly, that's the second rank tensor of this. It has 9 components, and by the way, again, these components are equal to each other. Remember, this one is a symmetric matrix. And so now, what's the definition of each one of these? The definition for Ixx is integral of the distance of the element to the x-axis squared. What is it? In 3D, if I have this object and I have this small element here and the mass of it is dm, and these are the x's, x, y, z, the distance of this element to the x-axis is what? If we project this down, we know that these are the x, y, and z components. So if I want the distance of this element to the x-axis squared, what should I square? I should square this y, and I should square this z, and add them together, which is going to be this distance. This distance is the distance of the element to the x-axis. This distance here. If I square that distance and multiply it by the mass of the elements, not the area of the element, that is going to be Ixx. Similarly, the distance of it to the y-axis is x squared plus z squared times dm integrated, and to the z is x squared plus y squared. And then the product terms, there are going to be 3 of them. So xy, Ixy, or yx is simply xy, and then yz and xz. Okay, you see that? And what are these negatives? Actually, we don't need to talk about these negatives right now, because this is the one that we use with negatives in the equations of motion for rotation. So the equation of motion for rotation is not as simple as this. It's a little bit more complicated. For translation, yeah, it's sum forces equals mass times acceleration at the centroid. But for rotation, the equation is a little bit more involved. Like what? Well, so this is the 2D example. This is the one that I just said. This is the simple rotation equation for 2D. But in 3D, the equation is like this. Sum of the moment, all of them, x, y, z, about the centroid is equal to the I matrix times omega dot, or alpha, and omega is the angular velocity, plus omega itself cross I omega. And this I here, which has a 3 by 3 dimension, and omega or omega dot, they are only 3 by 1. So this I here, this inertia matrix that you see, that is this guy. And in that, these off-diagonal elements, these product terms, they all have a negative in them. Okay, so there is this negative defined for them if you want to use these equations, which we call them Newton-Euler equations. And these govern your rotation of rigid body in 3D. And this term here, I omega, is what we call angular momentum with respect to the centroid. We call it angular momentum. By the way, these I's are all measured from centroid. In other words, you put the axis, you put the origin. When you calculate these I's, the origin of the frame should be at the centroid, just like these figures. Remember, look at these figures. The frame that you put X, Y, and if there is a Z, the center of that frame should be at the origin when you calculate these terms. So this I here actually has a reference. It is with respect to the centroid. And since this mass can move in all 3 directions for an arbitrary object, these are really triple integrals. All of these are what? Triple integrals, because both x, y, and z can change. So these are all really triple integrals. And clearly, you can see that I here is an inertia term, because if you remember in linear, for translation equations, the linear momentum P was mass times velocity. So momentum was what? Momentum was inertia times velocity. That's the definition of momentum. If you're moving faster or you have bigger inertia, you have bigger momentum. This is linear momentum. Right? Mass times velocity. A similar thing applies here to I omega. Look at that. Momentum, but this time angular momentum, equals what? Equals the inertia for rotation, times what? Times velocity, but angular velocity. That's the same thing. So these I's are inertia terms, which is resistance to rotation. And if you look at their units, the units are length squared times mass. So all of these guys, their unit is like kilogram times meter squared, or like, for instance, pound mass times what? Times feet squared or inches squared or something. And they show resistance to rotation. Now, for well-known shapes, these are some of the well-known shapes and their moments of inertia about their axes. So if you have a cylinder about this axis, just that component out of the 9 components, only that one, if you call it, for instance, Z, that is going to be your IZZ, is going to be 1/2 mr squared, where m is the total mass of the cylinder and r is the radius of it. For a sphere with radius r, or 2r in this case, radius r or diameter 2r, I'm sorry, radius r still, and mass m, I about this axis, again, if this is z, that IZZ is 2/5 mr squared. For a plate with mass m and width and depth of a and b, it's ma squared plus b squared over 12. For a slender bar which has only one dimension, really, the other dimension, this radius is very small. It's very similar to that, except only one of them is like, for instance, you're setting this A to 0, only considering B, which is the same as L here, then you see this formula becomes that. And if you have the cylinder, but you want it about this axis, so if this is y-axis and this is z, then Iyy is what? Iyy is 1/4 mr squared plus 1/12 ml squared, which is basically this term plus something like that, but not exactly. And you might say, what about the x-axis? If I had this x-axis, what is Ixx? Well, remember, the shape is symmetric about the x and y together. So this should be the same as Ixx. Okay, so these are well-known shapes, and you can calculate all of them by integral. For instance, I can easily calculate this one for you. The calculation of that is very similar to the rectangle, except you only have one dimension to go. So it is very easy to show that. Now, what's the relation between these shapes and these moments of inertia and the topic that you just saw earlier, these basically surface moments or second moments for the surface? Is there any relation between them? The answer is yes. Well, how? So for that, we are going to look at one of these shapes. For instance, let's look at the plate. So if I go ahead and look at the plate, what do I get? Let's look at the plate, see what is it that we can get. So let me clean this up. So this guy has some very small thickness, T, which is very small, negligible. And remember, the mass of it is m. So if I look at it in this axis, along this axis, whatever it is, let's call it y-axis, or z, let's call this z if you want. If I look along z, what would you see? You're going to see the rectangle. And this is your x, this is your y, and the dimensions are a and b. So if I ask you, what is polar moments for this shape, what would you say? JO. You say this is Ixx plus Iyy. And what is that? This is the integral of what? What was this? Y squared dA, and this one was x squared dA. So this is going to be the integral of x squared plus y squared dA, correct? Over a. Now, what's the definition of this one? What is this I? IZZ, what's the definition of it? Well, let's go back and look at it. That's the definition of it. Look here. Oh, sorry. Here. Look. Do you see similarities? This is an integral of x squared plus y squared dm. This is dA. Very similar, huh? So if I consider a small element here that has area of dA and look at the thickness of it, what's the volume of that? The volume of that element, if you look at it in 3D, if you look at this guy in 3D, the volume of this element, the volume of it, dV, is the thickness T times dA. So here I can write this as TdA. And if T is constant and I can bring it out, this is going to be T times integral of x squared y squared dA, which is exactly, guess what? It's this one. So what can I say? You're right. I can say that these polar moments for Z, this inertia moment for Z is the thickness T times what? Now that's the volume. I want mass. There was one thing we forgot. The mass is not TdA. It's TdA, that's the volume. You have to multiply it by the density rho as well, because that was just the volume. You multiply by density, now you got the mass. And if rho is constant and t is constant, you bring t and rho out. Integral of x squared plus y squared dA is that polar moment. So it's going to be this. So you see, if I had the second order polar moment and I multiplied by the thickness and by the density of the material, I can get this IZZ. So you see, these topics are what? Related. So bigger J moment means bigger inertia moment. Okay? And what was it? Let's just go back and look at it. What was this guy for this rectangle? So one of them was this IXX was B cubed A over 12. The other one was A cubed B over 12. Remember? So now IZZ is going to be what? It is going to be equal to, remember, it was rho times T times JO. So there's going to be rho times T. Now, both of these, they factor A and B. So I write it as AB over 12 and then A squared plus B squared. Right? That's what it is. Now, I want you to tell me, what is this guy? ABT, that's the whole volume of that plate. Multiply by rho, that's the whole density. So the formula is going to be M over 12. And then what? A squared plus B squared. Guess what? That's here. You see? So you clearly see how you can go from one to the other. Okay. The last thing we want to talk about is called parallel axis theorem. What is this one? So remember, in these tables that you find at the end of any statics or dynamics book, there are all these well-known shapes, whether 3D or 2D, and their moments of area and moments of inertia are shown. Okay? Now, sometimes you have to calculate moments of inertia or moment of area for scenarios where the axes that you want are not passing through the centroids. So look at here. This L shape is given to me with dimensions, and it says find the second moment tensor, which is IXX, IXY, and IYY. Find these guys for this shape with respect to which axis? With respect to this axis that is here. The X is at the bottom, the Y is on the left. Find it with respect to these axes. Well, the problem is, if you consider this L to be one single shape, the centroid is probably here. And even if I had a table that has L in it, which most of these shapes don't, these tables typically don't have, or this table, they don't have L in them. But even if they did, when they gave me IXX and IYY, the X and Y in those tables are like this. They are passing through the centroid. So they would give me I, X, and Y for this two axes, not these two. So the question is, if I have it with respect to these axes passing through the centroid, and if you don't mind calling them X prime and Y prime, so we don't mix them with X and Y, if I have I for X prime and Y prime axes, can I find them for these axes X and Y that are parallel to them? You see, X is parallel to X prime, Y is parallel to Y prime. Can I find them? For parallel axes, the answer is yes, and it is called parallel axis theorem. And it's not really hard to show, but it says that if X prime and Y prime are the axes passing through the centroid, and I know the value of the second moment for these X prime, Y prime axes, so I have these values here. And by the way, here you can call it Y prime if you want. If I know those, they are given for me in a table, If I want to find it for axis xy that are not passing through the centroid but parallel to those guys, all I need to add to those stuff from the table is, for between x prime to x, all I need to add is the area of the shape times the distance between x prime and x. What is the distance between x prime and x? It's called dy. So I square dy multiplied by a. Similarly, if I want to go from y prime to y, what do? I take the y prime, and then what? I multiply the whole area a by the distance between these two, which is dx squared. If I'm going to go from product to product, I multiply a, but this time, since there is x and y, I have to multiply both of these distances together to get it. And if I want to go from O prime, which is this point, the centroid, to O, this point, then again, I'll multiply a by the distance between O prime and O, which is what? D squared. So these four are called, especially the first three, these are called what? Parallel axis theorem, and you can mathematically prove that. It's not really super hard to show, but that's not my goal here, is to prove that. Okay, so this is to go from axis through the centroid to axis not through the centroid, but parallel to those. The centroid ones you read from these tables, which are at the end of your books, and use these extra terms to them, these quadratic terms, you add them in terms of distance, and you get your ix and y. Now to practice that, we're going to look at this example and solve it. So what do we do here? This shape, this L shape is given, and we are going to find these numbers. How do we do it? Well, we need to use the formula that we just learned earlier. We learned that for a rectangle with B and H, Ixx, and look, this X here is the same as the primes in those formulas. So this is like X prime, Y prime. The ones passing through the centroid, X is this formula, the one for Y prime is this one. And Ix prime, Y prime, since it's symmetric with respect to X prime, Y prime is 0. Okay, so if you have these three from the table for a rectangle, can I use it to find the one for this problem? The answer is yes. Now this is L, that's not a rectangle, but what you can do, just similar to the composite problems in centroid, if you look at my centroid video, I can break this shape into two rectangles. So I'm going to draw a line here. So now I have rectangle 1, which is this guy, and then I have rectangle 2, which is this one. And for each one of them, I can calculate the terms based on the formula from the table, add them together, and I get this. So look what I do. Ixx of the whole shape is going to be Ixx of shape 1 plus Ixx of shape 2. And this is another interesting thing, is if your shape is composed of several components, if you add the i's of the components, you get the entire I. You can simply add them together. Now, how much is Ixx1? How much is Ixx2? Well, for shape 1, the centroid of shape 1 is here. And for shape 2, let's draw it again. And for shape 2, it's also in the middle. We know that for rectangles, it's exactly in the middle. So that's centroid 1. This is what? Centroid 2. Okay? So for shape 1, I know it if my axes were here. For shape 2, I knew it if they were here. So how do I calculate this? We say, well, for shape 1, I knew it for this x prime. How much is it? And this is your shape. Based on the formula, it is this width, which is 1 meter, times the height. Now, height of this shape is 3. So it's going to be 1 times 3 cubed over 12. This is for x prime, plus what? Plus the area of this shape. What's the area of it? 3 times 1. Times the distance between this x prime and the x that you want, which is this. What is this distance from here to here? Let me use a different color. What is this distance? I need to know that. Well, if this is 3, this is 1.5 plus 1, that is 2.5. So the distance from this centroid to the x-axis is 2.5 squared. So this is what this is for shape 1. Now for shape 2, what do we do? For shape 2, the width of it is 3, the height of it is 1. So for this x prime axis, it's going to be 3 times 1 cubed over 12. Plus the area of this, which is again 3 times 1, times the distance between this x prime and this x, which is half, squared. So if I add all these 4 numbers together, I'm going to get what? I'm going to get my IXX. So you're going to get 10.9975. And since everything is in meters, it's going to be meter to the 4. That is your IXX. Similarly, when we go for y, again, we are going to write it as IYY of shape 1 plus IYY of shape 2. Now for shape 1, which is this vertical one, for the y prime axis, for the one passing through the centroid, we have the formula. It is going to be this 1 cubed times 3 over 12. So this is going to be 3. Let me use a different color. So it's going to be 3 times 1 cubed over 12. That's for y prime, plus the area, which is 3, times some distance squared. What distance? The distance between this y prime and this y, which is only 0.5. For shape 2, which is this bottom one, the IY prime is clearly what? It is this 3 cubed times 1 over 12 plus the area of it, which is 3, times the distance between this y prime and this y, which is 1.5 squared. So if you calculate that, you will get exactly 10 meter to the 4. And then if we go for IXY, very similar. This is going to be IXY of shape 1 plus IXY of shape 2. Now for shape 1, let's clean up a little bit. So for shape 1, what we need is IXY with respect to its centroid, which is Ix prime y prime, which is clearly 0, plus the area of it, which is 3, times dx dy. What are dx and dy? Here, the distance from x prime to x, which was 2.5, and then from y prime to y, which was just 0.5. So that is for shape 1. For shape 2, again, with respect to its center, with respect to this x prime, y prime, it's 0 plus the area of it, which is 3, times two distances. What are they? This x prime to this x, which is 0.5, and then this y prime to this y, which is 1.5. And if you solve for those, you are going to get 6 meter to the 4. There we go. So I found my number. So if somebody says, what is I tensor? It is going to be IXX, which is 10.9975, IXY, which is 6, IXY, which is 6, and IYY, which is 10. Done. This is your moment tensor here for this 2D shape. So hopefully you learned what you need to learn here about moments. Now there is a separate topic which is called principal axes, and that is the axis with respect to which the moments are maximum. Okay, and that is when you can rotate these axes and move them. So if I rotate these axes, my numbers are going to change, and the question is at what angle these moments are going to be maximum. So here, if I, for instance, in this shape, if I go ahead and rotate my xy axis and put them like this, for instance, this is to be x-axis and this is to be y-axis, my numbers are going to be different. And the question is for which one these principal ones are going to be maximum. And these products are going to be 0. Okay, we call them principal moments. And that is a separate topic. I don't want to get into that. Later, we'll talk about that when we talk about the Mohr circle and other stuff. But hopefully, other than that, I covered all of the things that you need to know about the moments, parallel axis theorem, and how to calculate them. Thank you so much, and I'll see you in the next video.